Okay, hello. Good day, everyone. Okay, I just wanted to make a video. This is going to be a session on thin lenses, right? I just want to give a brief overview for it. Okay, so but before we go into thin lenses, what I want to do is I want to look at mirror equation. Sorry, yeah. So for mirrors, what we've had before is that my focal point, there are two ways of writing equations for focal point or focal length. Sorry, focal length. The first one being it is simply 2 over r, right? The first one being the as a function of r, right? I can determine what's the focal length if I know what is the radius of the surface of the mirror surface. Now the second way of finding out focal length is actually 1 over 4 1 over f equals to 1 over u plus 1 over v. So if I know the object distance, and I know where the image of that object is formed, I can figure out what's the focal length. Now, why is it important to review this? This is because for thin lenses, we also have both of these equations, or at least a variation of both these equations. The first one being we actually have the Lensmaker equation, right? The Lensmaker equation for relating between radii and the focal length. All right, just to remind you, thin lenses is just a piece of glass which has been cut such that you have either concave or convex surface on both sides. So for example, if I were to say a biconvex lens, it would look something like this. It would look both surface, looking at it from the left and right, is going to be convex, right? If I look at it from the left, I see a convex surface. If I look at it from the right, I see another convex surface. Similarly, if I have a biconcave lens, it is going to be concave when looked at from both surfaces. So how do I find the focal length based on the radii, right? Radii being the plural for radius. Okay, I will have the refractive index of the glass or the lens. Okay, actually that would be a better idea. Let's just use lens instead. So lens over the refractive index of the medium that is in, right, minus 1. Multiply that with 1 over r1 minus 1 over r2. Now this is going to be a bit odd because some textbooks, they actually use 1 over r1 plus r1 plus 1 over r2, so that can be confusing, but for this session I'm going to use minus. All right, so what is r1 and r2? Well, r1 is actually the radii of the first surface, so this is r1, this is also r1, and then r2 is the radius of the second surface, r2, this is r2. okay, so now I have a function of I have an equation relating between focal length and radii. I would like another equation as well for focal length and object and image distance, and quite nicely that it actually looks exactly the same as the equation for mirrors, right? They both have the same equation. However, the sign convention is going to be quite the opposite. Okay, and we'll talk about this soon. Okay, we'll talk about this right after this. Okay, so it is at this point I want to look at 1 over f equals to 1 over u plus 1 over v. Now both situation for mirror and lenses will use this equation. However, the sign convention for both of them is going to be different. Okay, so imagine if I have a mirror, right? If I have a mirror, let's say a concave mirror, what happens is, let's say we have f here, what happens is if I send a light ray that is parallel to the principal axis, once it gets reflected, once it touches the surface, it's going to get reflected and crosses through f, like that. Now this is what we call, these solid lines are what we call real ray lines, right? Real ray lines. as opposed to virtual ones, which is dashed. Usually you use dashed. However, if we were to send, right, if we were to send this ray line, ray line, the back one, towards to a lens, so let's say we send it to a biconvex lens, right, and let's say we have an F here, right. If I were to send a parallel ray line here, parallel being parallel to the principal axis, right, the outgoing ray, once it touches the lens, right, is going to go through the lens and out comes the other side. So our convention will be consistent to this. In other words, my F is positive when the focal point and incoming light ray is in the same side. On the other hand, for lens, I will have F positive when the focal point and the incoming light ray, right, on opposite side. Okay, now for mirrors, this is a situation where we call it to be a concave. That's a horrible color. Let me just change that. Should I use purple? Yeah, sure. This is going to be concave. This is a concave mirror, and on the other hand, this is what we call a converging lens. Okay, same thing. Okay, U is not much of a problem. U is always positive if it's a real object, but we also have the other way around, which is, what about the image distance, or the image itself? Well, the image for mirror is positive when the image distance and the incoming ray on the same side, right? This is what we call a real image. On the other hand, for lens, I have a real image when image distance and incoming ray on opposite side. Okay, this is again what we call a real image. Okay, so please notice the difference. The mirror has F and V to be positive when they're on the same side as the incoming light ray. On the other hand, the lens will have positive F and positive V when they're on the opposite side of the light ray, incoming light ray. Okay, so this is a very important distinction to make so that you don't make mistakes when you do questions. Okay, so at this point I want to talk about types of lenses. These are the main types of lenses. We can see there are converging lenses as well as diverging lenses. Okay, so a double convex lens, which is just called a biconvex lens as well. Okay, and a plano convex as well as a convex meniscus, they're all converging lenses. What we mean by converging lenses is that their focal point is going to be positive, and as we've covered before, the focal length is positive when the focal length, the F, is on the opposite direction of the incoming ray. Okay, and quite the opposite for diverging lenses. You will have F less than 0, which means it's going to be a negative value. Again, we have a biconcave lens here, and a plano concave as well as a concave meniscus. Okay, now the biconcave double convex lens, if we were to look at where the radius are, let me just use purple and probably red. Yeah, okay, we can find out where R1 is positioned, right? R1 is positioned here, right? And then R2 is positioned here. So what that means is that my R1 is going to take, so if your incoming light ray, incoming is from the left, my R1 is going to be positive and my R2 is going to be negative. Okay, again, for all the cases I'm going to talk about, we will assume that the incoming is coming from the left. All right, things may differ if you were to talk about it coming from the other direction. Okay, all right, so let's look at plano convex. Right, if we were to look at plano convex, we can still see that R1 is still positive, right? However, because the next section is plane, this is called plane, is a plane mirror, a plane surface. What you will see is that this would actually have R2 to be equal to infinity. Well, yeah, approaching infinity. Mathematically speaking, it would be approaching infinity. Okay, approaching infinity. Okay, let us talk about meniscus later on. Let's just continue with the double concave as well as the plano concave. Again, I have, let's take a look. My first surface is going to be here in front, so my R1 is going to be negative, and then my second surface is going to be over here, which means it is going to be positive. Okay, quite the opposite of the double convex lens. Okay, now how do I know that? Let me just again clarify. How do I know that? Because the second surface is going to form a circle here. The first surface is going to form a circle here. Quite the opposite. On the other hand, for the double convex, it's going to form here. The R2 is going to form over here. Okay. And then again, the plano concave, I have R2 to be approaching infinity. And then I have R1 here to be negative. Okay. All right. So now we want to move on to the meniscus cases. All right. The meniscus cases. Okay. So when you do your problems, how do you know if it's a convex meniscus or a concave meniscus? Is it the orientation? Not necessarily. What you do is you look at the thickness of the lens. If I were to label this D1 and the width here to be D2, right? In the convex meniscus, I will have D1 bigger than D2. Well, once you see that D1, the middle, is bigger, is thicker than D2, then what you have is a converging lens, which means that my F is going to be positive. On the other hand, if I have it thinner, so if you look at the concave meniscus, I have D1, then I have here D2. This would mean I have D2 bigger than D1, and that indicates it is a diverging lens, and therefore my F is going to be less than 0. Okay. Okay. Now, but what do we mean by converging and diverging lens, right? What do we mean by converging and diverging lens? So a converging lens, right, is when you send a bunch of parallel incoming rays. So these are all parallel, right? And then once it goes through that converging lens, those light rays will be refracted such that they will meet at a point. So that means they will converge at that point. Okay, on the other hand, if we talk about diverging lens, when you send these parallel rays, they will diverge from each other, they will move away from each other, and they won't meet. Only their virtual lines will meet on the same side as the incoming light ray. Again, I want to remind you that for converging lens I have positive f, and for diverging lens I have negative f. Okay, so we've covered a few things, right? We've covered how we can determine the focal point or focal length using the radii of the surfaces as well as the refractive index of the lens, right? So I can have 1 over f equals to 1 over f equals to the refractive index of the lens over the refractive index of the medium minus 1, then 1 over r1 minus 1 over r2. Okay, and then the second one I have is 1 over f equals to 1 over u plus 1 over v. That is if you want to determine the focal length using object and image distance. Now, of course, once you have this, you want to make some conclusions about the image. So the third one that we have is the magnification. Magnification is no different than the mirror case. I have the height of the image over the height of the object equal to negative v over u, and both of that equals to m. Okay, so as I've covered before as well, if I have m bigger than 0, which means it's positive, right, it is going to be upright, and if m is less than 0, then I will have it inverted. The image is inverted image. Okay, and then if I have the magnitude of m, the absolute value of m, to be bigger than 1, then it's going to be magnified. Or if I have the absolute value of m to be less than 1, the image is diminished. Okay, of course we can also add a few more things, that if v is bigger than 0, it is real, and if v is less than 0, then the image is virtual. And these are the 3 main characteristics that you can look for.